Two non-parallel planes in three-dimensional space will always intersect along a line. Let's consider two such planes. In this diagram we illustrate a portion of each plane, which intersect at the dotted line. We'll call that line L. We'll also label the normal vectors to the planes. So this vector, n, is the normal to the first plane, and this vector, m, is the normal to the second. Now, recall that L, just like any line, can be described by a vector equation of the form r equals a plus lambda b, where a is a vector from the origin to L, b is a vector parallel to L, that is, it points along L, and lambda is a scalar that can take any value. So, if we can find two vectors a and b that meet these criteria, then we can write down an equation for L. In order to do this, the following fact will be useful. So, recall that n cross m, the cross product of the two normal vectors, is perpendicular to both n and m. We saw this in the video on the cross product. But if n cross m is perpendicular to both vectors, then it must be parallel to L. To see this, let's redraw n and m so that they both start at a point on L. So we'll put n here and m here. Hopefully now you can see that since n cross m must be perpendicular to n and m, then it must look something like this. The direction it points along L is determined by the order we do the cross product in. If we instead did m cross n, then the vector would point along L in the other direction. But this wouldn't matter since either way it is still parallel to L, and that's all we care about. Again, if you're unsure about this, you should watch the earlier video in this series on the cross product. Now, let's try an example. Let's try to find the equation of the line of intersection of the two planes x plus y plus z equals 5 and 4x plus y plus 2z equals 15. We know we're looking for an equation of the form r equals a plus lambda b. So let's find a and b. We'll start with b, which must be any vector parallel to the line of intersection. We can find it using the method we just described, i.e. by taking the cross product of the normal vectors to the planes. We find these vectors by taking the coefficients of x, y, and z from the plane equations. So, for the normal to the first plane, let's call it n, we use these coefficients. Hence, n equals 1, 1, 1. For the normal to the second plane, m, we use these coefficients, and we get that m equals 4, 1, 2. The cross product is therefore the determinant of this matrix. IJK 1, 1, 1, 4, 1, 2. We won't go into the detail of taking this determinant here, as we covered this in a previous video. Instead, we'll just state the result, which is I plus 2j minus 3k. So, as a column vector, b equals 1, 2 minus 3. Now let's find a. Remember, a is a vector from the origin to the line, so we just need to find a point on the line, and then we can use the vector of this point as a. Well, a point on the line would of course lie in both planes. So, we need to find a point x, y, z that satisfies both plane equations. To try to simplify things, let's assume that there is a point with z equal to 0, which lies on the line. Then the two equations simplify to x plus y equals 5 and 4x plus y equals 15. Solving these two equations simultaneously gives us x equals 10 over 3 and y equals 5 over 3. Again, we haven't explained this in detail, as simultaneous equations are covered in a video in the algebra series of videos. So, using these three values, we get that a is 10 over 3, 5 over 3, 0. Finally then, our equation is r equals 10 over 3, 5 over 3, 0 plus lambda 1, 2, minus 3.